Hello everyone, welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will emphasize on another teaching lesson which is Biot Savart's Law. Okay? In this Biot Savart's Law, it is a relation which gives a quantitative relationship between current in a conductor and the resultant magnetic field produced by this conductor in a space or region around it. Now, if we have any current carrying conductor, we know that there will be magnetic field lines associated or magnetic field will be produced by that wire. Say like for instance, I have this wire, let this wire be carrying a current I in one direction, and I have also another wire which carries a current I in the opposite direction. We know from Orsted's experiment, we have come across that any wire carrying a current, that means it will always produce magnetic field around its neighborhood. Now, it was due to this law, the Biot Savart's law, which laid emphasis on the relationship between current flowing through that wire and the magnetic field produced by it. Okay, and the magnetic field produced by it. So this law, it gives us a relationship between current I and the magnetic field B produced by that current element or any conducting wire. Now these two pictures are the pictures of these two renowned French physicists. Okay, both these scientists are from France. Okay? They are French physicists. Okay? They are from French physicists, and they are Biot and Savart. Okay? Biot and Savart. Okay. Now this scientist, the first figure is the picture of one scientist by the name of Jean Biot. Okay, Jean Biot, and the other picture, okay, will be the name of another scientist, French scientist by the name of Felix. Okay, Felix Savart. Okay, Felix Savart. Both these scientists, they collaboratively, okay, established this formula in the 18th century, which peculiarly will be in the year of 1820, very close to what Orsted's experiment found out, that there is a relationship between electricity due to the current I and the magnetic field. Okay, so this is one of the technological development in the field of physics, which gives us a relationship between the current produced by the wire, the current flowing through the wire, and the magnetic field produced by the wire. So both these two scientists, Biot and Savart, they collaboratively establish this empirical formula which gives us the foundation or the relation between current and magnetic field, or we can say it is a connection between electricity and magnetism. That is why it is because of this law that we have this new branch of physics which is also known as what? Electrodynamics. Okay? Electrodynamics or electromagnetic theory. Okay? Electromagnetism. Okay? Electromagnetism. This is one branch of physics because of the development of the relationship between electricity and magnetism. We have one branch of physics which is known as what? Electromagnetism. So in the exams, statement is important. Remember that this no need to prove Biot Savart's law, but it is only an empirical formula. Now, if I have this wire carrying a current I, okay, if I have this wire carrying a current I, that means I can consider many elements across the wire. Okay, suppose over here I consider this part of the wire and let dl be that length of the wire. Okay, be that length of the wire. Then suppose if I consider any point P, okay, any point P which is at a distance r away from this current element. That means from here when I say current element, that means this is that vector. Okay, IDL is our current element vector. Okay, IDL is the current element vector. So it will produce a magnetic field at this particular point. So the magnetic field produced at this particular point will be perpendicular to the plane containing the two vectors. So from here you'll have this will be your current element, and this will be the position vector of the current element and the observation point P. At this particular point, that means we have what? There will be magnetic field. Okay, there will be a small magnetic due to the current element dl. There will be a small one. There will be a small magnetic field at point P. Okay, at point P. So similarly, for the other direction also, we will have the magnetic field. Okay, we will have the magnetic field dB due to the current element. So which means that over here, if we want to find the magnetic field due to all the contribution, which means that each part of the current carrying conductor contributes to the magnetic field around him. Then if you want to find the net value of magnetic field B at any point, it is the combined effect. Okay? It is the combined effect of the individual part of the conductor. It is the combined effect of the individual part of the conductor. Yes, so that is one of the most important point that we need to understand. Then from here, the statement is that the magnetic field produced by this current element. Yeah, IDL. What is the current element? The current element is IDL of the conductor of length 1. Of length, what is the length of that element? The length of that element is dl. Then carrying a current I. It is given by this relation, which is also known as the inverse square law. So from here we have this relation dB equals sign mu naught divided by 4 pi. Okay, mu naught divided by 4 pi I dl sin theta divided by r square. This is an inverse square formula, which means over here that this is also like similar to Coulomb's law of electrostatics, which is an inverse square law. Okay, where this mu naught, okay, is what is known as the permeability of free space. Okay, this mu naught is what is known as the permeability of free space. Okay, let me write over here. What is this mu naught? This mu naught is the permeability. Okay, this mu naught is the permeability of free space. Okay, free space. And this mu naught has a value. Okay, this mu naught has a value which is equal to 4 pi. Okay, 4 pi into 10 to the power 7. Okay, 4 pi into 10 to the power minus 7. Okay, 4 pi into 10 to the power minus 7. 4 pi into 10 to the power minus 7 Tesla ampere inverse meter. Okay, Tesla ampere inverse meter. You can establish these units of what? These units of what? These units of mu cube. So that is the value of mu naught. This is the value of mu naught. Then further, it means that this expression which I have written over here, this mathematical expression is the what is known as your Biot Savart Law. Okay, this is what is known as your Biot Savart Law, and it is an inverse square law. That means it depends as inversely as the square of the distance. So from here you can establish, you can work out this proof of, and we know that the SI unit, okay, the SI unit of magnetic field, okay, the SI unit of magnetic field, the SI unit of magnetic field is Tesla. Okay, in honor of one Croatian, okay, in honor of one Croatian physicist by the name of Nikola Tesla. We will come into this discussion afterward. Okay, this is his name, Nikola Tesla. So the SI unit of magnetic field is Tesla. So if you work out, okay, if you work out the units of mu naught, so on the left hand side it is Tesla, capital T. Then over here we want to determine mu naught. Then I'll put as mu naught. Then current is ampere. Then dl. Okay, the length of that dl will be meter. Sin theta, it is a dimensionless quantity, and over here you have what? You have meter square. So meter and meter will get cancelled. So if accordingly mu naught will be equal to 1. Tesla. Cross multiply m this side, then you get half m, and cross multiply e this side, then you'll get what? Ampere inverse. So that is the way how to derive the relation. Okay. So next from here we will try to study how to find the direction of your magnetic field. Okay, how to find the direction of the magnetic field. So we can find the direction of the magnetic field by using this right hand palm rule. Okay, right hand palm rule. So on this figure, you have seen that there's a palm. The thumb will indicate, this thumb will indicate the direction of the flow of current. That means this is the direction of the flow of the current. And this outstretched fingers, all these outstretched fingers, okay, will indicate the direction of your what? Magnetic field. Okay, this will, outstretched finger will indicate the direction of the magnetic field, and this will be the direction of what? Of that force. Which means in this case, suppose if I take that this, okay, in this case we will take the direction, will not take the direction of B. We will not take the direction of B. First of all, okay, this outstretched fingers, okay, outstretched fingers will give us the direction. In this case, will not take the direction of the field, will take the direction of that position vector. Okay, position vector, direction of the position vector. This is a different situation. Direction of the position vector, and this direction to which the palm face. Okay, this is the palm, okay, the palm of your hands. The direction in which the palm face, that will give you the direction of what? That will give you the direction of your magnetic field. So this will give us the direction of the magnetic field. So from here, when you look at this first instance in which the current is moving upwards, okay, I have this current element dl, and this r will be our position vector of the observation point P. Then using this right hand palm rule, okay, this thumb, the thumb will indicate the direction of what? This thumb will indicate the direction of the current element, which means over here we have that IDL. Okay, this is your IDL. That means over here this palm, your palm is facing down. Okay, your palm is facing down. Okay, down the page, or over here down the screen. So your outstretched fingers, first of all, the first thing that you need to do is to align the position of the thumb in the direction of the current. Number two, the outstretched fingers, these outstretched fingers will be in the direction of what? Of your position vector. So over here we have that position vector R, which is this point. So the outstretched fingers, these fingers will be in the direction of what? Will be in the direction of PV. Okay, direction of your position vector PV. This thumb, okay, will be in the direction of what? The thumb will be in the direction of the flow of current. Okay, the thumb will be in the direction of flow of current. So that thumb will indicate your current. So first you place place the thumb in the direction of the current. Next, outstretch your fingers in the direction of the position vector R. Then the direction in which this palm face, okay, the direction in which the palm face, your palm, okay, the direction in which the palm face, that will give you the direction of what? That will give you the direction of your magnetic field B. So from here, this palm is down. This will be the direction of I, the IDL, that means current element IDL. Then next from here is that the outstretched fingers, these outstretched fingers will give us what? The direction of R. Then this palm is facing down, your palm is facing down. So the magnetic field at that particular point P, that means the magnetic field at this particular point P will be perpendicular and inwards. Okay, perpendicular and inwards. So if it is perpendicular and inverse, so it will be represented by what? It will be represented by a cross mark. Okay, over here it will be represented by a cross mark. So it will be perpendicular and inverse. So it is like a cross. It's like when you shoot an arrow. Okay, when you shoot an arrow, this tail of the arrow, that will give you what? The cross mark. Okay, so which means that at this particular point D, at this particular point P, yes, of course, the direction of the direction of this, that dB, okay, the direction of this dB will be 1, will be perpendicular. Okay, this dB will be perpendicular, but it will be perpendicular in one sense. Okay, it will be perpendicular in one sense. In the case that, it is 1, it will be perpendicular and 1 inwards, or perpendicular and inwards. So that is why over here, we will have to represent by what? By the cross mark, which means that over here, what does the cross mark indicate? That means it is perpendicular. Direction of B is perpendicular and inwards, or into the board. Over here it will be into the screen. Okay, into the screen. So next, when the current is moving in the opposite direction, downward, how will you find the direction of this magnetic field? Say, like for instance, at this point P. Okay, so that is the point P. The point P is at a distance R from a certain point O, which is at the current element. So from here, see, another important emphasis before we discuss this one, that means we have this current IDL, and from here, okay, this is our current element IDL. So this is that vector. If I expand like that, this is the current element IDL. So this will be the current element IDL. So that is the first vector. Then from here, there is some angle between IDL and R. So it's like this. Okay, we have this vector. So this vector is what? Is our IDL vector. Okay, IDL bar vector. And from here, this is our R vector. This is our position vector. Then there is an angle between I and DL, which is theta. So from here, the angle, okay, the perpendicular component of I and DL, that will give you sine of theta. Okay, that will give you sine of theta. Understand? So next, from here again, I can divide this vector, I can divide this conductor into many elements. And from here, suppose I consider this particular element. Okay, I consider this particular element, and let that element be one, be DL. Then this current element will be in this direction. So our current element will be in that direction. Okay? So this will be our one. That will be our current element. This will be the direction of our current element. In this case, this will be the direction of our current element. In the same direction in which the current is flowing. Direction of the current, this is the direction of your current element, IDL. So which means over here that IDL will be in the downward direction. So this will be your IDL. Okay? That will be the direction of 1. IDL vector. And at this particular point, this is your point P, then this will be 1. This will be the position vector R. Then this is the R bar, and this is your IDL bar. Then there is some angle between I and D bar, that will be theta. Yeah. So from here also, where you have to find out what will be the due at point P, due to this current element DL, there will be what? There will be magnetic field dB. Okay, there will be magnetic field dB at this particular point. But you need to know that since dB will be perpendicular to R bar and will be perpendicular to DL bar, so you have to apply this right hand palm rule. So when you apply this right hand palm rule, it should be, you have to orient, okay, you have to align and orient your right hand in such a way that this palm, okay, your right hand, your palm face towards you, okay, so your palm will face towards the palm, towards yourself, okay, palm towards yourself or palm towards you. When you align this finger, this is your right hand, okay, all this will be your right hand, okay, this will be your right hand. And when you align your right hand in such a way that your palm faces towards you, okay, faces towards you, and in this case the palm is facing down or away from you, then this thumb indicates what? The direction of your current flow. Okay? The thumb indicates the direction of the current flow, which from here also I have indicated that the thumb indicates the direction of the current flow. So this is our direction of current. From here also, this is the direction of current. So we have placed that thumb. All these outstretched fingers, okay, all the outstretched fingers will indicate one. This outstretched fingers will indicate this one PVR. that PVR. So this palm, okay, this palm is facing towards you. The palm, this palm is facing towards you. So that will give you the direction of your DB. So at this particular point, DB will be perpendicular to your page. Okay, will be perpendicular to the plane of the paper, or it will be perpendicular to the screen or the board. So in this case, we can represent this by this vector at this point. It will be perpendicular to R, this dB. Okay, of course, that dB over there, it will be perpendicular. This dB will be perpendicular to this dB. Okay, that dB over there, it will be perpendicular to this dB. It will be perpendicular to DL and R, but it will be in such a way that it is perpendicular and out of the board. Okay, out of the board. So you have to represent. How will you represent that? We can represent that at this point P, okay, by a dot. So that is the dot. This dot will indicate that it is 1. This dB, okay, this dB is perpendicular and upwards, or perpendicular out of the page. Okay, perpendicular and upwards. In this case, perpendicular and upwards into the screen. In this case, it will be 1 out of the screen. Okay, out of the screen. In your case, if you are writing on your paper or copy, it will be out of the page. In my case, it will be out of the screen. Okay, in this case, it will be into the screen. Okay, so these are the important emphasis. So this will be the direction. See, the current is moving in this direction. Okay, so you have to orient your your right hand in the direction of the flow of current, thumb in the direction of the thumb, outstretched fingers in the direction of R. So the palm is facing towards you. Palm is facing towards you. So that will be give you the direction of what? The direction of DB. So this DB will be out of the board. So this DB will be out of the board or out of the screen. So it will be represented by dot. Okay, it will be represented by dot. So this will be the right hand palm rule to find out the direction. So in this case, this angle between I and DL, okay, this will be the angle. This small angle over here below, okay, I will rub this one. This is your IDL. Okay, this is your IDL. This is the direction of IDL. Then this angle between I and DL, that will be what? That will be theta. Yeah, this will be theta again, so that you not get confused. Okay. So this is our element. This is your IDL element, and that angle over here, okay, this small angle over here, this small angle between I and DL, this IDL, this small angle between IDL bar and this is your one. This is your theta, the angle between R and DL. So in this case, IDL is like this. This is your R. This is your IDL, and this is R. That means this is angle 1. This is our angle theta. So from here, that is the, because magnetic, why we are stressing on the direction of B, because magnetic field is a vector quantity. Okay? Magnetic field is a vector quantity. So from here, what Biot Savart did is that from here we find out that there's one important implication that from Biot Savart's law, it is an empirical formula. That means magnetic field at the point P due to the current element 1, due to the current element IDL, and a distance R. Okay, from the Y is given by this relationship. Number 1, it is directly proportional to 1, the current element. Okay, directly proportional to the current element IDL, and which means there is dB will be proportional to this current element IDL. Okay, IDL. Next, number 2, it is directly proportional to the sine of the angle. Okay, sine of the angle between the current element and the radius vector. So which means that this dB is directly proportional. It is directly proportional to the sine of the angle theta. And next, from here, this angle dB again, this angle dB again is inversely proportional. Here this inversely proportional to the square of the distance. Here this inversely proportional to the square of the distance. So when you combine these condition number 1, okay, condition number 2, and this will be condition number 3. So from this 1, 2, and 3, it implies that this dB will be equal to what? This dB will be, first of all, we'll write proportional to sin. This dB will be proportional to ideal. Okay. Ideal. Okay. Sin theta divided by 1 divided by r square. Okay, divided by r square. Which implies from here that this dB, in physics we remove the proportionality sign, we keep the constant of proportionality. That constant of proportionality is k, okay, k ideal. If it is in free space, okay, if it is in free space, this value of k will take the value of mu naught by 4 pi. That means in free space, this value of k will take the value of mu naught divided by 4 pi. Okay, mu naught divided by 4 pi, which means that this dB, okay, this value of k, after replacing by mu naught by 4 pi, then we will get this relation. Okay, dl sin theta divided by 1 divided by r square. So that is the relation. So this is your relation. This is our relation. Okay, this is our relation. And this formula is what is known as your Biot Savart Law. But keep in mind that this relation, which I have written over here, this is Biot Savart Law in scalar form. Okay? In scalar form. We also have to represent this Biot Savart Law in vector form. Okay? So since why we have to represent in vector form? Because dB, our current element, our magnetic field due to the current element ideal, is a vector quantity. Okay? It is a vector quantity. Understand? Then from here, there are rules I have written over here. Okay, the rules for finding the direction of dB. The rules for finding the direction of dB is that the magnetic field I have expressed that it is a vector quantity. How do we use? We use this right hand palm rule. We use the direction. We use to find what? The direction of the magnetic field of that observation point. Then you have to the thumb will indicate, the thumb of the right hand points in the direction of what? Current flow. Then the outstretched fingers points in the direction of your position vector or the radius vector. Then the direction where the palm faces, that will give you the direction of your magnetic field. So over here also I have written that if the direction of dB is perpendicular and into the pitch, perpendicular or into the pitch, or the palm faces into the pitch or into the screen, then the direction of dB at that point P is perpendicular and inwards, and it is denoted by the cross mark. It is denoted by the cross mark. Now, if the direction of dB, if the direction of dB faces down, and which means that dB at that particular point will be represented by a dot, that dB at that particular point will be represented by a dot, which means it will be towards you or towards the reader. Then the direction of dB at that point is perpendicular outwards, or out of the page or out of the screen. And in this case, the direction of dB is indicated by what? By that dot mark. Okay, dot mark. So another important thing that we need to understand is the Biot Savart Law in vector form. Okay, Biot Savart Law in vector form. Now this Biot Savart Law in vector form, in scalar form we have already been introduced that the direction of dB is what? Mu naught by 4 pi. Okay, mu naught by 4 pi ideal sin theta divided by r square. Okay, r square. Now the direction in vector form, this direction, this magnetic field is given by this expression dB bar this will be equal to 1. Mu naught divided by 4 pi. Okay, mu naught divided by 4 pi. Mu naught divided by 4 pi ideal cross r cap divided by r square. Why I have written like this? Because when you look from this relation, okay, when you look from this relation, that means if you look from that relation, we have, this is our dB, and we have one, we have ideal. Then we know that r cap is any unit vector. Okay, r cap is any unit vector, which means the magnitude of r cap is always 1. Why? Because this is our unit vector. This is our unit vector. So if I multiply this by the r cap, or if I take this will be what, the cross product, since ideal is the cross product. So over here this will be r cap, okay, sine of theta divided by 1 divided by r square. You have that quantity of 1, mu naught by 4 pi. You have that quantity of mu naught by 4 pi. Then from here, mu naught divided by 4 pi. Okay, mu naught divided by 4 pi. Then from here you have IDL. Then from here, this, okay, it comes from the definition of the cross product of two vectors, A cross B. Okay. A cross B will be what? Will be A B sine of theta. Okay, sine of theta n cap. Okay, so that n cap will be our r cap. So this will be our A vector. This will be our A vector, or the first vector, and this r cap will be our one, our second vector, which means that over here this will be nothing but what? Ideal cross r cap divided by 1 divided by your r square. So this is the way how to write the expression of what? Of dB in terms of what? Vector form. Yeah. So that is why it allows me to write this expression. It allows me to write this expression. Then next, we also know that the direction, that this definition of this the definition of this r cap, which is the unit vector, the definition of r cap, which is the unit vector, or I hat or r hat, this will be r bar, okay, r bar divided by mod of r, okay, r bar divided by mod of r, or in this case we can simply write r bar divided by r, okay, r bar divided by r. This is the definition of one of the unit vector, the position vector divided by the magnitude of its vector. Okay, so from here this dB can be expressed in scalar, in vector form. We can express this dB. Once we express in vector form, remember to always write down the bar notation. This will indicate the vector notation. Then over here you have what? Mu naught divided by 4 pi. Okay, mu naught divided by 4 pi I dl. Then what is this r cap? This r cap will be what? Cross r, from here, from this relation, okay, from this relation it will be r bar divided, we have over here you have the term containing r square, and from here also you have what? We have another r. Then finally this will give us the expression of what? dB, okay, dB bar equals sign, okay, dB bar equals sign mu naught divided by 4 pi I dl. Remember to put the bar notation. Over here IDL bar cross r bar divided by 1 divided by your r cube. Remember, in Biot Savart Law, in vector form it is in terms of cube, okay? In scalar form it is in terms of r square. So this is the formula. This is the formula for Biot Savart Law in vector form. So this is your what? This is our vector form of Biot Savart Law. Vector form of Biot Savart Law. So from here, let us represent those importance. From here, we have this is your figure. Okay, so the current I is moving in the upward direction, and from here I will consider any element dl, which means this is our current element idl. So in this case, I have to represent this by a vector. Okay, I have to represent this by a vector. But before we represent that, let us take any point P. Okay, let us take any point P. Let us take any point P, and then let that point P. Okay, let this be the point P, and let that point P be at a distance r away, which means that in vector notation we use the radius one as r bar. Okay, this is our r bar. And from here, this is our current element, and then the direction of the current element will be represented by this vector. Okay, by this vector, we will represent this by this vector. Okay, we will represent this by this vector, and we'll take this vector, and this vector will point on this direction. Okay, this is your ideal vector. Then next, okay, next, that means the direction of this, it is represented by that. This is the direction of one, that will be theta, and in this direction, the direction of this r bar is represented by that unit vector r cap. So at this particular point we have one, at that particular point we have the magnetic field. Remember, you have to use that right hand palm rule. Okay, you have to use that right hand palm rule. You have to outstretch your fingers. Okay, this will be the direction of I, and this will be the direction of R, and then your palm is facing down. Your palm is facing down. Okay, your palm is facing down. So at this particular point, okay, at that particular point, the magnetic field, since it is facing down, is perpendicular and into the screen, so it is represented by cross. So which means, okay, it is represented by 1. It is represented at that particular point. It is perpendicular. It is perpendicular and into the board or into the screen, so it will be represented by that cross. So it is here represented by cross, and from here, since it is perpendicular, so we will take this vector and represent it over here. We take this vector and we will represent at that point P. So that is the direction of 1. That is your direction of dB. So this will be direction of 1. Direction of our dB. Okay. This is direction of dB. This is the direction of dB, perpendicular and upwards. Okay, so that is the illustration with regards to Biot Savart Law in scalar and vector form. Always remember that the SI unit of magnetic field is in terms of Tesla. Okay, it is Tesla. Why it is in Tesla? Because the SI unit is named after one Croatian physicist by the name of Nikola Tesla. This person is very important in the branch of electromagnetism, and it is because of him that we have this technology of about what AC currents. Okay, and from here he is the one who pioneered this electromagnetism. He invented the AC motors and explained the concept of what AC current. So from here, point number 1. Okay, point number 1 is focus. It needs more attention. The SI unit of magnetic field, of course, it is Tesla, denoted by capital T. Okay, denoted by capital T is of course the SI unit of one magnetic field is Tesla, denoted by capital T. But for recording the values in our day-to-day life or experimental value, we use non-SI unit. Okay, non-SI unit, because why? This value is very large. Okay, it is very large. We often use in terms of non-SI unit, which is Gauss. You must have come across this word of Gauss, okay, from Gauss law of electrostatics. Then we know this. Keep in mind that before we do this, okay, this value of Tesla is very large, okay, which means that Tesla is larger than Gauss. Okay? Tesla is larger than Gauss. Okay? One Tesla, okay, one Tesla will be equal to how much? One Tesla will be equal to 10 to the power minus 4 Gauss. Okay, 1 Tesla is equal to 10 to the power minus 4 Gauss. And when you look from these values, this is the conversion. This is very, very important. 1 Tesla is 10 to the power minus 4 Gauss. And in our real situation, suppose we know if we want to find the magnetic field of the Earth, okay, this is the magnetic field of the Earth is of the order of 3.6, okay, 3.6 into 10 to the power minus 5, okay, minus 5 Tesla. This is the magnetic field of the Earth. We know that the Earth is also rotating about its own axis. It will generate magnetic field. Okay, it will generate magnetic field. Then this is the value of the magnetic field of the Earth. But the magnetic field of the Earth is tremendously very large, which is equal to 3.6 to 10 to the power minus 5, which means that over here, if I want to express this in Gauss, I can do that. Okay, I can express this as 3.6. Then over here I'll have what? 10 to the power 1, and over here this will give you what? 10 to the power minus 5. That will be Tesla. And if I keep on finding, okay, if I keep on finding, that means over here this will give you what? This will give you 0.36. If you calculate this, that means it will give you 10 to the power minus 4. But if we keep on simplifying, okay, that magnetic field of the Earth will be 3.6. What is this 10 to the power 4 Tesla? 10 to the power 4 Tesla is nothing but what? It's nothing but Gauss. Okay, one Gauss of this. Sorry, there is some mistake over here. Okay, there's some mistake here. One Gauss is 10 to the power. One Gauss is 10 to the power minus 4 Tesla. So this is what? This is in terms of what? This is in terms of Gauss. Okay, one Gauss. Okay, so this is very important. And why is it very large? From here you can find out that we know that one Gauss is 10 to the power minus 4 Tesla, which means that over here, if 1 Tesla, if you even cross multiply this to the denominator side, that means it will give you 10 to the power 4 Gauss. So which means that it is 1. 1 Tesla is very large, which means that Tesla is very large than Gauss. This of the order of how much? 10,000 times. Okay, 10,000 times. Then this is the practical implication of the various magnetic field due to the Earth. Also, if we can break down some information about the magnetic field B due to human nerves. Okay, human nerves. Even our human nerves also, human nerve fiber also, they produce some magnetic field. Okay, the recorded value of the magnetic field due to human nerve fiber is about 10 to the power minus 10. Okay, 10 to the power minus 10 Tesla. So these are the values. Okay, next we will study about some of the special cases of magnetic field B. Okay, magnetic field B using Biot Savart Law. Now the first case is that we will study this in terms of the current element ideal and the the position vector r. So from here, when the angle between the current element ideal is perpendicular to the radius vector 1, to the radius vector r bar, which in this case, okay, I have this figure. And on this figure I pass a current, and this current is moving in this direction. Then I consider any element, let that element be dl, and this will be the direction of our IDL. I consider any point P, in such a way that the distance from this point up to the point P, that will be our radius vector or position vector r bar. Okay, that will be our radius vector or position vector r bar. So this is your r bar. And from here it is obvious that this angle ideal and that r bar So this is our r bar vector. This is our IDL vector. Over here, the angle between IDL and r bar is how much? It is 90 degrees. So this right angle of perpendicular. So this is our angle theta, which is equal to how much? Which is equal to 90 degrees. Okay. So from here, if we represent this, okay, if we represent this, this is our IDL bar vector. So this is our IDL bar vector. I'll make it quite longer. This is our IDL bar vector. Okay, that pink color is our IDL bar vector, and at this particular point also, we know that by applying that right hand palm rule, it is perpendicular and into the bone. So this is represented by cross. Okay, so this is represented by that cross. You have to apply that right hand palm rule like that. Okay, this is the direction, the palm. Okay, the palm indicates the direction of what? The palm indicates the direction of I. Outstretched fingers, direction of R. Palm facing down. So this cross. So this will be the direction of DB, perpendicular and inverse. So we will have to find out what will be the direction of this DB at that particular point. Okay. So it will be like that. So in this case, we know that the value of dB bar, this will be equal to mu naught divided by 4 pi I dl. Okay, IDL will just calculate only the magnitude. Okay, we are interested in the magnitude, so we'll use the scalar form IDL, then sine. In this case, since this and this are equal to, since IDL and R are perpendicular, it means that the angle between them is how much? The angle between them is 90 degree. Okay, 90 degree, which means that over here this will be sine of 90 degree, and over here this will be what? This will be r square. So we know that sine of 90 is how much? Sine of 90 is 1. So we'll get that the mu naught, okay, IDL. So that will give, this will be the value. Okay, this will be the value of dB, which means that the magnetic field, if the angle between IDL, our current element, and the radius vector are perpendicular, so the magnetic field will be maximum. Okay, it will be maximum. So in order to get maximum magnetic field, so the direction of our current element and our radius vector should always be what? Should always be perpendicular to each other. Next, let us consider the case in which the angle between the current element IDL, the angle between the current element IDL bar and our radius vector R bar are in the same direction. So over here, use the same concept. This is the direction of I, or this is the direction of your current element flowing through a conductor. Then at this particular point, okay, we will take the point P, which is along the direction. Okay, so which means that if I consider this element from here, if I take that as our DL element, this is our current element DL, then our IDL also will be on this direction. Okay, so from here, see what will be the direction. Okay, what will be the direction of DL bar? So this will be what? That pink color, this pink colored dotted line will represent what? Will represent our, this pink colored vector will represent our what? This pink colored vector will represent our this pink colored vector will represent our what? Our position vector R bar. So over here, let us write this as what? This as R bar, which means that over here IDL, okay, this IDL and this R bar are in the same direction. Okay, IDL and this R bar are in the same direction. So what will be the direction of B? We know that since it is in the same direction, so let us try to find out. So from here, since they are in the same direction, so from here, which means if I draw properly, this is the direction of ideal, and from here using that pink color vector, that means in the same direction, this is the direction of what? This is the direction of R bar, which means that the angle between them is how much? The angle between them will be equal to 0 if they are in the same direction. So theta will be equal to what? Theta will be equal to 0 degrees. So from here, that means this, let us represent this vector. This will be the vector of what? This will be the vector of ideal. Yeah. So we will find out, okay, what will be the direction of dB. Okay, what will be the direction of dB? So in this case, this special case number 2, dB, using the scalar form mu naught by 4 pi, so mu naught by 4 pi, so over here this will be ideal. So sine of the angle between current element and radius vector, so the angle between them will be 0 degree if they are in the same direction. So over here this will be, we know that sine of 0 degree will be how much? Will be equal to 0, which means that when you take the point, okay, when you take the point P along the same direction, so the magnetic field will be equal to 1. The magnetic field will be equal to 0, which means that there will be no magnetic field, on the point near the conductor, on the point near the conductor, okay, near the conductor. So this is one important application. Then next, suppose let us consider that the angle between the current element ideal, the angle between the current element ideal bar and the radius vector r bar, are antiparallel. What do you mean by antiparallel vectors? That means if I consider this as the first vector, and if I consider another vector as the second vector, when I say antiparallel, which means that the angle between them is how much? The angle between them is 180 degrees. So these are some of the important things between antiparallel vectors. So from here again, we will consider the direction to be the same direction. Okay, direction of the current I flowing in the upward direction. This is the current I flowing in the upward direction. Okay, current I flowing in the upward direction, and then we will consider the point, okay, the point P, okay, the point P in this direction. Okay, current I in the upward direction, and the point P is in the downward direction. Or in this case, this current I is in the upward direction. Then I will find out this point P in the opposite direction, which means that opposite to P. So let us take this as the point P, and I will take the current element from here. Okay? So let us take this current element in the opposite direction. Let us consider that the current is moving in the upward direction. This will be the current element, and from here, okay, let us consider the current element to be in the upward direction. Okay, upward direction, and I will be in the downward direction. Okay, so this will be the direction of I. Okay, that will be the direction of I. And then this I will consider the DL bar. This will be some current element. So this will be the direction of IDL. Okay, that will be the direction of this will be the direction of IDL will be in the since this is the direction of I, so IDL will be in the upward direction. Okay, IDL will be in the upward direction. Then next, what you have to do is that suppose if you consider the point P in the downward direction with respect to this IDL, then which means that over here, if you take this vector, that means if you point at that particular point, so which means that over here, that if I represent this, okay, if I represent this ideal by this orange vector, okay, this orange vector, that means over here, I'll take this vector and I'll put it over here. That will be our one. That will be our ideal vector. This will be our ideal vector. So that is our dl bar. Keep in mind that the direction of I is in the upward direction. The direction of I is in the upward direction. Over here, I consider this wire, and direction of I is in the upward direction. This is the point P. So this will be direction of 1. This will be direction of IDL. IDL should be in the same direction with respect to I. And then this is the point P. And from this current element, downwards, that means in this direction, that will be 1. That will be our radius vector R, which means that from this point up to this point, that will be R bar. So our R bar will be in what? In the opposite direction. So which means if I draw separately, this is the direction at this particular point, okay, at that particular point. At this particular point, this is the direction of our IDL current element with respect to this current. And from this point, with respect to the observation point P, okay, with respect to the observation point P, this is 1. This is our radius vector, which means that the angle between these two, is how much? It is 180 degree. Even from here also, if you calculate the value of dB, it will be equal to 0. So from here, this work out, this will be mu naught divided by 4 pi, okay, mu naught divided by 4 pi IDL, okay, sine of 180 degree divided by 1 divided by r square. Even sine of 180 degree is equal to 0. So dB in this case, okay, will be also equal to 1, will be also equal to 0, which means that if we want to find magnetic field, okay, the point, the angle, over here also there will be no magnetic field, okay? Over here also there will be no magnetic field, which means that if you want to get magnetic field, the angle, okay, what is the summary over here? The summary over here is that the direction of IDL, okay, the current element should always be perpendicular. The current element should always be perpendicular to 1. The current element should always be perpendicular to the radius vector R, so that dB is not equal to 0 or non-zero. Okay? Not equal to 0 or non-zero. So this is the most important thing that we need to understand. Remember that this Biot Savart law is nothing but an inverse square law. It is an empirical formula, which is the formula obtained by analyzing these current elements and the magnetic field. Also keep in mind that another important thing is that any current carrying wire, okay, any current carrying wire will produce what? Will produce magnetic field. Okay? Will produce what? This will produce magnetic field. This will produce magnetic field in the region surrounding it. Okay? This will produce magnetic field in the region surrounding it. So just go through those lectures so that you will understand. Okay? Until we meet again, thank you.